Dr. Nazin Shah. My name is Navalina Analaki Toyraj. My matrix ID is 211291020. Today we're going to discuss about LEF4 frequency response to Bode plot. The objective of this experiment is to be able to use MATLAB commands for Bode plot analysis and to understand the Bode plot analysis. So as for the first procedure, this is the graph or schematic diagram, which has two inductance value, 2 ohms and 2 Fahrenheits. This is the circuit. And this is the calculation for the circuit. So we'll be using the GS equals to VOS over VIS formula. And this continues. And as it continues, this is the final value with K over 4S cubed plus 4S squared plus 1. So this is the table whereby this is the theoretical value and the actual value from simulation. So for the gain margin is 15 in theoretical value and the actual value is 20. The phase margin is 66 and the actual value is 68.2. The gain crossover is 0.5 and the actual value is also the same 0.5. The phase crossover is 0.4 and the actual value is 0.0964. And this is the procedure. When k equals to 0.1, this is the formula. Numerator is 0.1. The denominator is 4410. This is the formula. And this is the Bode diagram. So as for this, the gain margin is 20 dB. The frequency rate of 0.5 radian per seconds. Is the closed loop stable? Yes. And the phase margin is 68.2 degrees. The delay margin is 12.3 seconds at the frequency rate of 0.0964. Is the closed loop stable? Yes. So the system was shown to be stable in both the semi-log graph paper and simulation. This is because both approaches yielded positive values for both gain and phase margin. For both approaches, the phase margin is larger than the gain margin. As for procedure 4.2.2, this is the calculation. When k equals to 0.1, the calculation goes on and goes on. This is the table. If the value of 0 is negative 20 dB, and this is 0, this is 0, the total value is negative 20. As for 0.5, this is negative 20, negative 20, negative 20, the total is 0, negative 16. Same goes for another 0.5, same value applies. And this is the Bode plot. And the continuation of the previous calculation when W is equals to degrees, 0.1 W equals to 112.62 degrees, when 1 equals to negative 216.87 degrees, when 10 equals to negative 264.28 degrees, when 100 equals to negative 269.43 degrees, when 1000 equals to negative 269.94 degrees. So as for exercise 4.1, a positive gain margin represents the extent to which the control system gain can be augmented, whilst a negative gain margin indicates the extent to which the control system may be diminished. Hence, the difference in answer to this, the control system must meet both negative and positive gain margin and the phase margin requirements. And this is exercise 4.1.2. When k equals to 100, numerator is 300 and 300. The denominator is 1, 57, 360, 500, 0. This is the coding. The peak gain is 396 dB at the frequency rate, and the gain margin is 35 dB at the frequency rate of 17.5. Is the closed loop stable? Yes. And is the phase margin is 96.9 degrees. Delay margin is 2.48 seconds at the frequency rate of 0.681 radian per second. Is the closed loop stable? Yes. And the Bode plot demonstrates a system with favorable stability characteristics exhibiting a peak gain of 396 dB, a substantial gain margin of 63.6 dB, a sizable phase margin of 96.9 degrees, and a delay margin of 2.48 seconds. So this is the calculation. And when k equals to 50, we are getting 150 and 150 as a numerator. The denominator is 157, 360, 500, and 0. This is the peak gain, 390. The gain margin is 41 at a frequency rate of 17.5, and the closed loop stable is yes. And the phase margin degree is 94.5 degrees and delay margin is 5.32 seconds at a frequency rate of 0.31 radian per second. The Bode plot generator with K equals to 50 reveals a system with peak gain of 30 dB at a frequency between 1e to the negative of 20 radian, a gain margin of 41 dB at 17.5 radian, a phase margin of 94.5 degrees and a delay margin of 5.32 seconds at 0.31 radian per second. So this is the calculation when K equals to 50. When K equals to 500, the numerator changes to 1500 and 1500. The denominator is 157, 360, 500, and 0. This remains the same. So as for the Bode diagram, the system is G, peak gain of 410 dB at a gain margin of 21 dB at frequency rate of 17.5 radian per second. At the clue stable is yes, and the phase margin is 56.9 degrees. The delay margin is 0.234 seconds at a frequency rate of 4.24 radian per second. Is the closed loop stable? Yes. The Bode plot generator with K equals to 500 depicts a system with a peak gain of 410 dB at a frequency between 1e negative of 20 radian. It possesses a gain margin of 21 dB at 17.5 radian per second and a phase margin of 56.9 degrees and a delay margin of 0.234 seconds at 4.24 radian per second. So this is the calculations. And when K equals to 1500, the numerator value changes to 4500 and 4500. The denominator remains the same. The peak gain is 419 at a frequency rate of 1e to the negative 20. The gain margin is 11.5 at a frequency rate of 17.5 radian per second. Is the closed loop stable? Yes. And the phase margin is 26.5. The delay margin is 0.05233. And the frequency rate is 8.68 radian per second. Is the closed loop stable? Yes. And the Bode plot generator with K equals to 1500 exhibits a peak gain of 419 dB at a frequency range of 1e to the power of negative 20 radian. It showcases a gain margin of 11.5 dB at 17.5 radian per second and a substantial phase margin of 26.5 degrees. The delay margin is 0.053 seconds at 8.68 radian per second. This is the calculation for 1500. And this is the calculation for 4.1. When K equals to 100, this is what we get. And this is the discussion. And this is the I'll demonstrate in MATLAB. This is the value for 0.1, the rundown. So this is the graph. So this is the graph. So then we'll be going for when the value is 100, this is the coding, and this is the graph. Here, here. So when the value is equaling to 50, so this is the value for 50. Now this is the value for 500. So this is the value for 500. And this is the value for 1500. So value for 1500. So with that, thank you for listening.